So you've been using these things a bit. What you haven't been talking about is how to route these IP addresses, and we're going to get into this a lot more, especially when we get to the Cisco part, which I think at least half the class is probably going to be doing tomorrow, because I see you people racing through this certification, which is good. So remember in good old IP version 4, there was class A, B, and C, and then after a while there was /27, /30, and /16 and all that stuff. So you didn't know how much of the address was for the network and how much was for the host. But in IP version 6, that is all over. 64 bits for the network, 64 bits for the host, that's it. That was the whole point, because that's why they didn't compromise and go to a 64-bit address. They went all the way to a 128-bit address, so you will never have any lack of addresses again. You'll never have to worry about conserving them. So you can just draw the line right there. So the routers only care about this much, and the rest is for the host. And the recommendation for companies is, when you sign up for IP address service, you should get a /48. That's what ISPs are supposed to give you if you're a normal company. If you're a huge company, they give you something even smaller. But they give you a /48, and then you have 16 bits for subnets. You can have 65,000 subnets, and every subnet has an unthinkably huge number of addresses, 2 to the 64, the square of the entire IP version 4 space. So you will never have to combine 2 subnets to make them bigger. The idea is you will just number your stuff and it will just sit there. One other, by the way, really nasty thing is if you change internet service providers, you have to renumber all your devices. This is what they are saying in IP version 6. Now, I am very skeptical about this, but the point is, remember, IP version 4 originally made sense. Originally, there was nothing but Class A. There were only a possibility of 250 possible networks. Then they split it into A, B, and C, and the routing table got bigger. Then they split it into CIDR, so everybody split their A, B, and C allocations all over the map. So now the backbone routing table has 400,000 entries, which is utterly insane. Every packet that has to traverse the internet has to be examined by each router, compared to a list of 400,000 routes to choose the best route to forward it, which is completely insane. The IP version 6 backbone only has 2,000 routes. And when fully expanded, it will only have 20,000 routes, and supposedly it won't grow because of this rule. Supposedly, people are going to have to stay with their ISP, and therefore, giant aggregate routes like /23s will be all you need to route to the right ISP. So a small number of giant aggregate routes will route most of the traffic, and it will be much simpler. We'll see what really plays out. I have a feeling that people are just going to fragment anyway, whether people like it or not, and they're going to refuse to renumber their devices, but all that's in the future. But the original plan is that your global routing prefix comes from your internet service provider, and if you change ISPs, that will change, and you'll have to renumber all your devices. Now, you're supposed to be automatically numbering them anyway. You don't use DHCP in IP version 6 very much. It is available, but it is not recommended. What's recommended is SLAC, stateless auto configuration, whereby the only thing the routers advertise is the routing portion. They advertise the first 64 bits with routing advertisement packets, and the hosts just make up their own interface ID, which is typically just a random number. That's what's recommended, and that would make it easy to renumber all your devices, because this part is done locally anyway. You just change the routing advertisements on the server, and everything's renumbered. The problem is, there's no way to distribute the DNS server. So you still need DHCP just to distribute the DNS, and this seems to be like a dirty little secret. There's a lot of shockingly poor features in IP version 6. Just obvious, simple things are just missing, like what to call these little parts of the address. You know, it's incredible how much of it is not really ready for prime time. It's just barely working and thrown out, and we're going to really start living on it, where a lot of things are not working. Anyway, that's the game. This is the plan. So globally routable addresses assigned to somebody. See, here's a subtlety which I didn't really know about IP version 4. There is the legitimate addresses, which are assigned by Ayanna and Aaron and such. And then there are darknets, people using addresses without the approval of the proper authorities. There are people squatting on other people's addresses. There are people using addresses that are not assigned to them. This is why, as you exhausted the pool and started handing out the undesirable addresses, one of the undesirable blocks they were never going to hand out was 1. The address is starting with 1 because it's full of spam. There are people using that address, and there's a lot of noise in that address. One of the most, the address 1.1.168.192 is getting some enormous amount of traffic constantly because of people that have typed in IP addresses backwards. in devices. And there's another one of them that is getting an unbelievable amount of busy signals from misconfigured telephones. Voice over IP phones are actually sending a bunch of traffic to a non-existent one address. So when people actually got the one block, they found that it was hard to use. Anyway, so the same thing's going to happen here. So you could just pick an IPv6 address and use it. But if you want to have one that is actually assigned to you, that will stay with you, you have to use the official IANA ones, and those all start 001. The first 3 bits are determined. So that is 1/8 of the IPv6 space set aside for globally routable IP addresses. There are a lot of other ones set aside for special purposes. All right, so here's the format. You know this. There's 8 words or fields or whatever they end up being called, which are 16 bits each, and you typically write them in hexadecimal. And you can omit leading zeros in each field. So this 0008 can just be 8. And once in the address, you can put in a double colon, which means fill in with zeros until you have the right size. But you can't do it twice, of course, because that would be ambiguous. And colon by itself is all zeros, 128 zeros. By extension, that's a logical interpretation of it. So that's a sensible way to do it. So here's the game. This address 2001 00000003F can be written this way, 2001 : 3F. The loopback address in IPv6 is 127 zeros and 1. You may remember a stupid policy in IPv4. They took an entire class A and with 16 million addresses and burned them to have the loopback address, of which we only need 1. And right about now, we could use those 16 million addresses. This was a poor design decision. But back when they did it, there seemed to be plenty of addresses. So they're not making that mistake in IPv6. The loopback address is assigned 1 address. That's it. The unspecified address is : And remember, that's what you folks are all used to seeing now. If you're running, if you're doing your certifications and you have a web server or an email server running, then you will find it here with netstat -an. And if you go back, you will find that you are listening, like I am running the web server, : 80. Another questionable design decision is, back in good old IPv4, we used the period to separate the numerical fields. So you could specify a port number with 10.7.202.179 : port number, right? That's the plan. And you can put that in the URL of your web browser and everywhere else. Well, you can't really do that in IPv6 anymore because we use the colon here. So you have to put square brackets around it in order to make it unambiguous. And you can actually go to IP addresses directly that way. Since I'm listening on port 80, I guess I'm serving a web page on port 80. Let me bring one up here. I should be able to see it a variety of ways. Let's try it this way. 127.001. Okay, I'm set up an IIS server just like you folks. Now I also have a GoGo6 tunnel running, like you do, I think, and should have a local IPv6 address. Maybe I can't find it. I think the GoGo6 tunnel is running whether you can see this utility or not. The utility just lets you administer it. Right, so I'm connected. So there's my IPv6 address. So I can go directly to this IPv6 address, copy, and I can put it here, but you have to do it this way. With brackets, there. And notice how the browser compressed it. It removed some of the zeros and it put in the : And I can also, of course, put in the port number here, : 80. This is Chrome, by the way, so you're not seeing the HTTP at the start. It's there. It just doesn't show it to you in Chrome. So they took away the 80 because it was redundant. But that's one little trick of IPv6 because of another questionable design decision. It might have been better if they'd chosen to use a semicolon or a comma or something to separate the fields in IPv6 addresses instead of reusing the colon that had already been reserved, but that's the way it is. So that's the game here. This address, 2001 001 0003F, cannot be reduced with double colons because that would be ambiguous. You don't know whether to put 4 zeros here and 1 here or 3 and 2 or anything, so that's not really unique. You have to choose to either do it this way, put these zeros in explicitly in a double colon, or put those zeros in explicitly in double colon. That's as short as you can make it. Now this, if you think about a software developer, this is probably already beginning to be a little disturbing. This is beginning, think about how you'd have to write your code to hunt. So far you're going to have to handle leading zeros, fill them in. Well, that's not too bad. Then you're going to have to find this double colon and figure out how much to fill in by counting how many other fields there are. Now that might seem okay, but you can give yourself a good headache with IPv6 to IPv4 addresses. This is for the convenience of companies that wish to preserve their existing IPv4 numbering system and convert to IPv6, and so they want to have IPv6 addresses that are simply related to their IPv4 addresses. This is a generic format, and the way it works is you have hexadecimal for the first 6 fields. The 6th field is FFFF, and then you have dotted decimal for the last 32 bits. So think about what a headache this is going to be for your programmers. Sometimes they're going to write this mess using dots or using colons here, and then you're just supposed to know that this is really 192 decimal to be converted to binary 8 bits. It is not 0192 hexadecimal, which is a completely different thing, 16 bits long. And you're just supposed to somehow deduce that. Anyway, that's the, that is a acceptable IPv6 writing format, which is easy enough for humans to read if you know your IPv4, but going to be a headache for your software developer. So there's the game. Decimal here, hex over there.
So that has to be, the hexadecimal part, that has to be dots instead of colons?
No, you can do it this way too with colons. But then you have dots on the right. You aren't allowed to put colons over here. Yeah.
First, however many bits, 90-something bits.
96 bits. It's 96 bits of hex and 32 bits of base 10. Pretty rude. So here's the loopback address, and so you can use that. It's probably the sort of thing to do once or twice just to get used to how funny it looks. Ping. Let me make this thing a little smaller so it goes higher on the screen. Because, all right. So I can ping. That. Or I could have just pinged : : 1, which would be the same thing. That's the game there. That's the equivalent of 127.0.0.1. All right. So here's some types. The unspecified address is all zeros. The loopback has a 1, but all the rest are zeros. Now, FE80. If you go to Windows 7 or Vista and you do ipconfig, there are two weird, irritating things about it. The first thing is that Windows makes up a bunch of virtual adapters called tunnel adapters that don't seem important, but they make the thing scroll by too fast. Those are all the automatically configured IPv6 to IPv4 tunnels, which Microsoft attempts to make, including these ISOTAP ones, which in practice don't work very well, but Microsoft does attempt to set them up. Then Teredo, which Microsoft does use to good effect. Microsoft uses Teredo for remote assistance now. That is how it is able to route from inside NAT and a firewall out to get help from other people. And then when it's done with all the tunnel adapters, you have your Ethernet adapter up here. Now these are VMware adapters just because I have virtual machines on here. Let me get to my real, there's my real connection to Collin. This is my real wireless connection. And so I have IPv4 addresses that came from the Collin DHCP server, and then I have an FE80 address, FE80 : : and then a bunch of hogwash on the right of that. 64 bits of hogwash because it has 4 fields, 16 bits each. So the first bit is the network portion, FE80, and then 3 fields of 0. That's a special address. That is an auto-configuration link local address. It does not route out of your local area network. It's used only locally. You can't route them on the internet. And you'll see them on every adapter. Now take a look at my real IPv6 interface here, my GoGo tunnel. My GoGo tunnel has FE80, which is link local address, and it also has a publicly routable address starting with 2001. That means it has 2 addresses on the same interface. You got to get used to this. Everything is always multi-homed in IPv6. Multi-homing is something you only do in IP version 4 for unusual purposes, like one machine sharing several websites, or for load balancing and things like that. But in IP version 6, it is expected that every machine shall be multi-homed. Unfortunately, client operating systems do not actually handle this very well. So in fact, one of the selling points of IP version 6 was you would now have end-to-end addressing. You would never have network address translation anymore. And this is the official doctrine, and many people will say it, but in practice, it's already completely going away. We already are used to NAT 4 to 4, IP version 4 to IP version 4. There is NAT 4 to 6, there is NAT 6 to 4, and there is now NAT 6 to 6. The Internet Engineering Task Force hates it, and they want to stamp it out, but people are already building the devices and using them because the two parts of their network with different IP version 6 routing prefixes cannot communicate properly over them because it doesn't properly handle multi-homing for some of the operating systems. So people are building NAT 6 to 6 devices, and if that becomes popular, it will be pretty much the end of the only remaining carrot in IP version 6. This is why IP version 6 is all stick and no carrot. The only reason to do it is because you have to, because they ran out of IP version 4 addresses. Now that is like Microsoft Vista. You know, the reason why everybody hated Vista is because Microsoft took all the good parts of Vista and gave them away free and called it Windows XP Service Pack 2. All the stuff in Service Pack 2 was supposed to be in Vista, but the security mess was so bad with Windows XP that Bill Gates, against the resistance of his own company, demanded to give away all the goodies free to the XP users to make the Windows machines work better so that everybody didn't just get fed up and all go buy a Mac. And it worked, but it killed Vista, because Vista was a whole lot of new hardware, a whole lot of work for your programmers for no real benefit. There was nothing much you could do on Vista that you couldn't have done on Windows XP anyway, and that's the way IP version 6 is. The good stuff in IP version 6, like IPsec, has been backported to IP version 4, like not multicast, but anycast. Anycast is where you specify an address. It's not one machine. You'll go to any of this pool of machines. Find the nearest one in this pool. That's now been backported. 196.88.99 is an anycast IPv4. So anyway, that's the game here. And if we do NAT 6 to 6, which may be the end result of all this, then IP version 6 will be just as much of a mess as IP version 4. But at least we won't be running out of addresses all the time. That's one thing. Anyway, so all right, here, let's see what else we got here. That is the link local unicast. Notice this is an FE80/10. The first 10 bits are specified. The other 118 bits can be anything you want. It isn't even cutting on a word boundary or on a, so this is 2 bytes. It's not even inside a hex digit. Remember, a hexadecimal character is 4 bits. So this cuts the hex character in half, cut it to /10. I don't know why they couldn't just cut it on a /12. By the way, you people seem pretty far ahead in the DNS, so let me mention this one. When you get to reverse DNS, you have to make a reverse DNS file. Now you may remember this, if you've done this in IP version 4, your reverse DNS file, let me get my word made bigger here, font. Okay, make it bigger so people can see it. All right, so if I have a DNS record, I might have an A record, and it might be, say, 10, let's make it 147.144.1.212. Okay, if I want to have a reverse DNS zone, I have to make a file that is 212.1.144.147.in ARPA, something like that. I might have got the details a little wrong. Remember these things? You have to make a file where the file name contains the address, and inside the file is the reverse resolution. You have to do the same thing in IP version 6. But when you do, there are like 2 or 3 different ways to describe that file, and the most popular one is hexadecimal. So if I was to have a reverse DNS record, which you are going to eventually set up towards the end of this certification process, if I find my GoGo 6 client, which for some reason I can never see anymore, I guess I keep closing it or something. When I go for it, it's gone. It used to appear down in the corner here, but somehow I'm not seeing it when I need to. Okay, here is my IP version 6 address. So the file for reverse DNS resolution is going to be that address backwards in hex. So this ends in E944. So the file I need to create is going to have a file name of 449E2000 and so on, and then in ARPA. And because you have to do it that way, you can never have a reverse DNS lookup for something that doesn't end in a slash number that's divisible by 4. So if you were to have a domain, a address range that ended with a /10, you could not resolve it with reverse DNS lookup. There is an alternative way to do this, which didn't work when I tried it to pass this certification exam, but in principle, you can make a file name which is reverse in binary, 128 digits. You can have a file name, here it is in 44, so that's 0100, so it's 0.0.1.0, 0.0.1.0. Okay, that's the first 2 of these, 4 and 4. In the same spirit, I could go 9E until I have 128 bits, one by one here, then in ARPA, and then that would be my domain. That's what reverse DNS would look like. But that didn't work when I tried it. I kind of imagined this probably overruns something in Windows. This is pretty horrible. This is horrible enough. Anyway, that's why I just thought I'd mention, in principle, you can cut it anywhere you want on your local domain, but in practice, you should divide everything with even multiples of 4. Have a /60, a /64, a /56, a /48, things like that, or you will get in big trouble when you try to do reverse DNS resolution. Anyway, multicast is FF. This one, thankfully, they cut on the boundary of a single hexadecimal digit. So FF, anything is multicast. There is no broadcast, not anymore. Everything is multicast. And there are a lot of different multicasts. There's a multicast address for all routers, a multicast address for all nodes, and a series of other ones. Of course, someone smarter than me would have to explain to me in words of one syllable what the difference is between a broadcast address and a multicast address for all nodes. Those sound very similar to me in practical effect. But in any case, technically, they are all multicast. There's no more broadcast. And then everything else is global unicast. You can use whatever you want, but if you want to have it assigned to you and reliably yours, you've got to have it start 001 and get it from the registries. That's the game. So here's the link local addresses. They start with FE80, but because this is only partway through a 4-bit word, FE90 and FEA0 are also included, because those involve changing these bits here. In fact, FEB0 would also be included, right? Because that'd be 3 plus 8 is B. Yeah. But FEC0 would be 1100. FEC0 is not included. So FE8, 9, A, and B. Okay? You know how to do your hex to binary. That's the game there. These are like the 169.254, the addresses that your machine makes up by itself when it tries to do DHCP and it fails. But even when DHCP works, or when you configure a static address in IPv6, you will still have an FE80. Every link always makes up its own FE80. It's used for local traffic. That's the game there. And this is used for neighbor discovery and auto address configuration. It's used so that everything can be communicated with even when you are not sure what address to put on it, when you're trying to put an address on there, when you're trying to check to see if the address has already been used. So everything has to have an address right from the start, so every node always makes up one of these. That's why every node is always multi-homed. All right, here's the global unicast. Wait, I think it seemed to have gone back, or am I using my mind? Link local. Yeah, the IPv4. Oh, yeah, here's the IPv4 map. Remember, we've seen these before. They look like this. A lot of zeros, 16 ones. That's the FFFF. And then 96 bits are all specified here. By the way, this is a notation you'll see for routes. This is where you have only the first 96 bits specified here. The other 32 are a variable. This is like an aggregate route. So here's the way you express this situation, that the regional internet registries are going to only hand out addresses starting with 001. It is 2000::/3, which it is, this is the route address with all the host bits set to 0, and this is the slash number that tells you how much of it is fixed. So the first 3 bits of that mess are fixed. So is 3,000 included in that? Any votes? What does 3,000 look like in binary? Let me try that. Yes, if I have 3,000 binary, well, I've just started something by accident somehow. All right, if I have 3,000 hexadecimal, what's that look like in binary? 0011. Then what's the next byte? Then it's all zeros, right? There we go. Therefore, let's compare that to the pattern. Shift F5. All right. There. And you can see it fits the pattern, 001. So 3,000, things starting with 2,000 and things starting with 3,000 are globally routable assigned addresses. That's how you read this nomenclature. And since you folks are Cisco types, you're probably ready for it, although it is a bit of a stretch to go from 0 to 128 instead of 0 to 32, but it's exactly the same principle. And you don't have to do any of this nonsense of converting it to base 10 anymore. So in fact, it's a lot simpler after you get over the original shock of seeing these big numbers. All right, so here's how you can configure an interface. You can manually put IP addresses on your interface. You may not have done it, but your interfaces have it just like they always have. If you go here to your network interface, Network and Sharing Center, here's good old adapter settings. Here's my wireless Cougar LAN adapter. If I go to properties, we've all been going here to this IP version 4 property sheet for a long, long time, but there's now an IP version 6 property sheet sitting there, and you can just type them in if you like. And you can even give it a prefix length or whatever you want. I guess I'll give it 64 and default gateway and all. You can put manual addresses on your interfaces if you like. It's not too popular a choice, but it is an option, and you'll do some of the packet tracer projects tomorrow with them if you're up to those things. Anyway, that's the wrong slideshow. Here's slideshow. Okay, there's the right slideshow. All right, that's one way. Auto configuration is the recommended procedure, where they let the interface make up its own ID. Unfortunately, it does so in a way that in retrospect was probably not too wise. You do have DHCP version 6 available if you want. You can hand out IP addresses, and you can hand out other things like DNS servers, which you kind of need with DHCP version 6, but you will need a DHCP client on the host, and you won't have that with Windows XP. That's why, to avoid having a lot of headaches, just use Windows 7 when you get your students on IP version 6. You can do it all on Windows XP, but it gets irritating. Then there's pseudo-random interfaces, which is privacy extensions here and cryptographically generated. Those are other ways to create a number there. So we've seen this. Everything typically has 2 addresses, multi-homed. And it even tells you here, this is the link local address, and this is the other address. There used to be 4 address classes. Now there's only 3. Here's how it generates its own address. This is called the Extended Unique Identifier. In order to get a unique number, it used the MAC address. The MAC address was supposed to be unique anyway. For some reason, which I cannot explain, instead of using the MAC address intact, they split it in half and put an FFFE in the middle. A lot of things for special addresses in IP version 6 like to have FFFF or something like that. They put FF at the start for broadcast, for multicast. They put FFFF before the IP version 4 address, so they seem to get a big kick out of these Fs. But anyway, why do they put it in the middle, I don't know. But this is what you do. And then for some reason they made modified EUI64 where they changed 1 bit in it. There is 1 bit in the MAC address that is not really used the usual way. I know that. There's a whole bunch of invalid MAC addresses. Not all 48 bits can be anything you want. One of them is always 0 or something. Maybe somebody out there knows this better than I do, but I know it's true. One of the bits out of the 48 actually has some other meaning. Anyway, so this is what you're supposed to do. EUI. The problem with this is, you people may be too honest to notice this, but the problem is if you were to do anything naughty on the internet, like criticize your boss or download a copyrighted music or something, you might not be happy to realize that you sent them your MAC address. They're already having enough success prosecuting people based on IP address, but if they had your MAC address, you'd have a really hard time explaining that that wasn't you, that was somebody else. So in retrospect, it's probably not a good idea to take your end-to-end IP address and put your MAC address in it, really. And this is such a bad idea that even Microsoft, who not generally regarded as a champion of security and privacy, did not implement this. They implemented privacy extensions by default in Vista and Windows 7. And so what you'll see is not a MAC address, and I can show you right here. This is Windows 7, and I have not turned this feature off, although you can. So if I do ipconfig/all, and I better pipe it through more, or it's going to really scroll off the screen and annoy me. There's my GoGo adapter. There's my wireless connection. Now I have a custom MAC address. I configured it in the registry of the machine. Well, I actually just did adapter properties because the City College wireless network used to restrict you to only 2 MAC addresses per student or teacher, and I have like 6 or 8 machines, so I just give them all the same MAC address all the time. They got kind of mad at me when they found this out because I tried out, this is actually not a valid MAC address. It violates that rule of whatever that 1 bit on the left can be. So after about a year, somebody actually noticed and busted me, and I had to explain myself. But anyway, that's my MAC address, AAAAABBBB, so I can remember it and put it on every machine I ever use. And, but if you look at my IP address, it does not have that pattern. It should be AAAAAA, BBBBBBB, FFFE, BBAAA, but it's not because privacy extensions are turned on by default. So in fact, it makes up random junk to fill that in, which is probably a lot better in the long run. And in case some other machine should choose the same random junk, which is, by the way, unthinkable because it only has 1 chance in 2 to the 64 of that happening, unless you have a lousy random number generator, which is possible, there is a duplicate address detection process where before you use an address, it says, is somebody already using this address? That's why you need the FE80 address around so you can communicate with people for that kind of resolution. Anyway, by the way, I should mention in practice something I cannot thoroughly explain, but you might want to know it. I used to have a project back when I taught Windows XP where students would learn what a duplicate address is. They would go to a machine, configure a manual address, turn it off, go to another machine, configure the same manual address, turn it off or disable the interface, turn them back on, and when they turn them back on, they get this error message. IP address already in use, and the one that comes on second gets a 0000 and it can't get on the network. So I handed out that homework. After upgrading the lab to Windows 7, it doesn't work anymore. You can configure 2 machines in a LAN like this with the same IPv4 address, and it works just fine. There's no error message, and they're both on the internet getting email, surfing the web. When I tried to figure out how is this possible, I went to the router, and the router's ARP cache keeps alternating from one to the other. Each of them is only getting about half the packets, but in practice you don't notice that. But there's no error message. The project didn't work. The only way to make it work is to do it with IPv6. If you configure manual IPv6 addresses in Windows 7 and turn on the machines, it will pop up an error every time. It checks for that. But it no longer checks for IPv4. And when I looked at Wireshark, there's a thing called a gratuitous ARP that is supposed to be sent when you bring up the interface, and it doesn't seem to do it for IPv4 in Windows 7 anymore, which I think is a bug. But anyway, that's a fun fact about that. So here's an example. There's an interface MAC, and therefore the IPv6 interface ID will be this: 004063 CA9A20 with FFFE in the middle. All right, that's the game of that. All right, so I have a few of these questions. Yeah, good.
The MAC address, isn't that just for the link local addresses?
Well, the MAC address,
I mean, used as part of it.
it is, no, it's used for every address. It's used for your public addresses too, not just for the link local. It's used for the host portion of each address. If it was just for the link local, then it probably wouldn't matter, but the point of this is you're not supposed to be running DHCP. You're supposed to be running router advertisement, which only tells your computers the first 64 bits. So they have to make up their own host addresses. That was the plan. That's why it was, the idea was nobody can remember these stupid addresses. What are we going to do? We'll just make it so you don't have to know. The machines will just make up their own addresses. And therefore you won't know or worry about it. That's the plan.
So the machine itself gets an IP address when you're on a network?
When you're on a network, it gets the first 64 bits by router advertisement, and it makes up the rest. That's how this normally works, unless you configure DHCP. By the way, there are some security nuts that want to think, remember there's some people that think NAT is a security boundary. because people can't see your network. Now, one thing about NAT is no one can run an unauthorized server, because if they're listening on a process, there's no way for an external person to send a SYN to that process without passing through your router. So that's the security in NAT, is if you get infected with a botnet and it tries to phone home, it can't send the trans back to control it, because it can't directly address that machine. But the other thing people say is it conceals your internal network structure. And that, and you can find, anyway, one thing about IPv6 is supposedly it conceals your structure now because you can never do a ping scan of a network. You could never try all the addresses in the network block. There's 2 to the 64 of them. Nobody has that kind of time. So you can't scan a network to find all the hosts anymore. The only thing you can do is neighbor discovery, which is very much like ARP, but that only works on the local network. You cannot do that remotely. Anyway, all right, any other questions? I'll pull out these response systems and let me see if I can get them working. I believe, let me see if I'm already running the application that picks up those signals. It looks like I am not running it. Let's see if I can find it. There it is, turning point anywhere. Okay, turning point anywhere. Theoretically, you people can vote. What does this do? Start. Okay, here, press a button. You have buttons like A through F on those little tiny doodads I gave you, and there should be what, 8 or 10 of you? 2, 4, 6, 8, 10, 11. No, just 10, I guess. Only 2. It's not working. 3. That's progress. Wonder if I can show this while you're voting. Looks like, oh, there we are. 6. Good. So I've, yeah, hit any button. Yeah, just hit A or anything, just so I can see that everybody's got it. 8 people have got it working. That's pretty good. Hopefully every one of you has those things and they work. Did I give you one? Good, okay, good. That's good. All right, so something close to everybody having one that works. That was my goal. Okay, let me see if I can get this thing out of my way and ask you some questions here. Okay. All right. So, which one of these is invalid? Is it? Yeah, well, then vote on it. You should have A through E on your things there. Just click it, and then you'll see, in fact, 9 answers. The answers are already up. 9 are up there. That's good. All right. So, good, 10 answers. Everybody answered. Good, let's see. Stop it. All right, that's, whoops. What happened there? Whoops. Vote again, sorry. I accidentally stopped the polling. I'm clumsy with this thing. There they come, 3, 6, 7, 8. All right. Yep, E, of course. That's what that's showing. That's pretty good.
E is invalid?
Yeah, E is answer 5. But E is invalid because, why is E invalid, folks? 2 double colons. You don't know, it's ambiguous. This 2001 this 2000 part could be sliding over any number of words, and you wouldn't be able to tell from that kind of notation where it belongs. All right. You can see up here the total number of responses, that's all. And there should go up to 10. So if it doesn't, otherwise than that, there is no feedback. As far as I know. Now, the ones I have in my class are different brand, and they actually have a light that flickers. And it flickers red if it didn't work and green if it worked. These things might have something like that. Try watching this time. And let's see, because these are new to me. So again, which one of these is invalid? Let me get this thing to start. There. So right, 0 responses. Okay. Good Lord, what a mess. Who wrote this thing?
You said invalid.
Yeah, which one of these? Apparently only one of these is invalid. Yeah, but the responses are coming. So it does have a green light when you vote? Yeah, that makes sense. That's the way the other ones work, because that's going to be a big issue for students, you know, in a big classroom, which is the point of these things. I like the way they're compact. Man, mine are in a big, heavy case, like a suitcase. So I get 7 answers. Guess I'll wait a little bit longer, see if I can get up to 10. 10, all right, good. So if I stop it, it shows the thing automatically. Good, so I see votes all over the place. Well, does anybody wish to defend? Go ahead.
C is wrong because they got G's up there.
That's right, that's the only problem. You can't have a G. Hexadecimal, 0 to 9, A through F. G is not allowed. The rest are all fine. Now, some people might think there's something wrong with this one. What's wrong with this one? Some people might not like 299, but that was IP version 4.
Wow.
When it was 299 going to go into 8 bits, this is 0299 hexadecimal, which is a perfectly valid pattern of 16 bits. This horrible mess is not binary, but it's perfectly fine. It's a bunch of zeros and ones. This is one of those ridiculous IP version 6 to IP version 4 mapped addresses that mixes decimal and hex together, but it does so correctly, insofar as such an appalling piece of junk could be correct. And this is not the loop back, but it's a valid address, 1 followed by 127 zeros. It's kind of strange address, but it's valid. All right. All right. Where's the loop back? I don't think those spaces should be there. I didn't mean to put them there. That was Word trying to clean up my grammar, I think. That's what you need, grammar checks when you're typing in junk like this. Anyway, so let's see what we got. A winner. The winner is number 2. That sounds good. Number 2 is indeed the loopback address, written out the long way in hex, not binary. In binary it'd be even longer, hard to fit on the slide, but all right, that's the loopback. You know, I wonder what would happen if you did that, really. In a proper network, it would loop over to IPv6 and be interpreted as IP version 4, and you might see the IPv4 loopback, I don't know. But you remember, you can, one of the first things I did when I first installed Windows Vista, I went to a class, they gave us the book, I immediately installed it on like 3 machines, and then I turned off IP version 4 to see what would happen, and we could totally network and share the local printer and everything over IP version 6 only. It prefers it. I thought that was pretty cool. And if you did that, I think this would never work. The only way it could ever work is if you have 6 and 4 running together. Anyway, all right, I want the largest link local unicast IPv6 address, and I've, for your convenience, repeated the pattern which specifies link local unicast up there. This is a Cisco subnetting question. I gave all my Cisco Exploration 2 students a bunch of these IPv6 subnetting to see if they really had it. And it kind of, they started whining that it was giving them a headache. But mostly got it right. And I told them, you're going to have to get used to it. Anyway, so, I see a couple more responses. One more response would be good. I'll wait like 10 seconds and then give up. All right. 9's what I get. Okay, let's see if there's any unanimity. Not really. Looks like the first and fourth are popular answers. Okay, the first one is a popular answer. Does anybody have any comments about this? What about this 0? Where are those zeros? They're way over here, right? This is FE 8, 0. I got a bunch of zeros over here. Therefore, they're beyond the network portion of this route, if you want to look at it that way. I could turn those to 1s, and I'd still be in this range. So this is not the largest one. I can change more bits. How about this one? You don't like this one either. Why?
It doesn't have the last 0 on it.
That's right. It doesn't, well, it does have the 0, but it has 2 more zeros after it. Because this is FE8. 8 is 1000. Okay. And if it's an 8 here, then these 2 bits are 0. And and to get the largest address, you have to change all these bits to 1. So when you do this, becomes 1011. And what's that? 11. And what's that in hex? B. So it's not there. Hey, did I foul up? I did foul up. There's no right answer. It's BF, isn't it? BF is the largest one, right? Did I foul up? I did, didn't I? FC, yeah, FE-BF. Why? Yeah, well, who wrote this junk anyway? So, well, I might as well fix that so that the next students don't get tortured the same way. I can have some different torture. So, here I thought I was so clever, but I think I'll just change this to B and that one to C. There. All right, fine. Good thing I'm not grading you on these. All right, on we go. All right. Anyway, hopefully it serves the purpose of letting people think this stuff through. How about the largest unique local address? These are addresses that are they're not supposed to be routed, but they are supposed to be unique. They're supposed to travel through your network, but not out onto the internet. I don't quite understand why they're different than the FE80s, but they're there, FC00s. There used to be 3 different kinds of non-routable addresses: site local, link local, and unique local. And it confused everybody so much that they finally got rid of the site local. Now we just have to understand the difference between unique local and link local, which I can't answer at the moment. But I think link local is only to be used with packets that will only go 1 hop. And these are allowed to go on hops to your enterprise, but not to the internet. I'm not quite sure. Anyway, what's the largest one? FC00/7. Hopefully I got this one right. Let's see. And this looks like I include all possible options, so one of them is very likely to be correct. Oh, 10 answers. Good. You people have figured out which one's correct. It's more than I have. Well, the most popular answer is number 3, although there's a lack of unanimity. FD, because FD would be, there's only 1 bit, so D is 1101. So I like FDFF. FEFF, E is 1100, right? So, no, E is 1110. 1110, and so it doesn't fit the pattern. But D is the largest one that fits the pattern. Okay? Anybody got comments or complaints or anything, let me know. All right, what's the largest address assigned to regional internet registries? Again, I think I got so many choices there, one of them might even be right. Six answers. Got a few yet to come. Yes, I'll wait another 10 seconds or so and then quit. We have a few abstainers. All right. The most popular answer is the second one, I think. Yep, which is, I think, the one I like. No, not the second one. This was the most popular answer. Well, fie upon you. That's not the right answer. What's the right answer? C, right? This, 2, is 0010. And you are allowed to change that to a 1, to 0011. Because remember, the largest one is where you have this, and all the rest are 1s. So 0011, that's just 3FF. Fie upon you. That 2 is 4 bits, and it's only a /3, so only the first 3 bits of that 2 have to be preserved. Okay? This is the, all right, I don't know if I got any more of these or not. Let's see. I do have more of these. How many different global routing prefixes are there? These are all math. Oh, good. A lot of answers have come in. 4. Well, I don't think any more are coming. Oh, here comes one. Let's see what we got. Whoa, all over the place. No great unanimity, whatever. All right, so let's talk about it. The most popular answer is correct, 2 to the 45. You have, for globally routable addresses, they all have to start 001. You have 45 bits to specify the global route. This is all not part of the global route. So you have 45 bits, 45, each one of them can be 0 or 1. There are 2 to the 45 of them. And So, you know, they claim the IP version 6 routing table will only grow to 20,000, but in principle it could grow to 2 to the 45. But the point is, by keeping it organized, they're planning to have nice giant subnets, you know, like /23s that route everything to Comcast and everything to AT&T, and just not too many of those will be needed to sort everything out. And in this spirit, I'll show you something as soon as this is over. I think I got another one. All right. I think this one was even in one of your tests there. Every company gets a 48 address block, or they're supposed to. So how many 64 subnets can they make? /64s. I see 5 answers. I see. Okay. 4. There comes some more. All right. And the most popular answer is number 3. And that's right, 65,000, because you have 16 bits, and that's 256 times 256. There's 65,000 possible combinations of those 16 bits. So your company can have 65,000 subnets, each unthinkably huge. And hopefully you will never have more than 65,000 subnets in your network, and no more than 2 to the 64 devices on each one of those, and therefore you'll never have to renumber your network either. That's the plan. But when people tell me you won't have to renumber something because it won't become a mess, I feel like there's a general law of entropy on the other side of that statement. But, you know, anyway, and so we'll get back to this stuff later. The only thing I wanted to show you, if I can find it, is the backbone. So let me show you a couple of stupid BGP tricks. Since I mentioned the backbone of the internet a couple times here, show you a couple fun BGP tricks. I think I've got them here. Yeah, there we are. Here's a couple of them. Here's an IP version 4 BGP tricks anyway, and I might be able to find my IPv6 BGP tricks a little later. But anyway, here, here's a command line on a Cisco router on the BGP backbone, which is kind of nice. Ah, this is the one I was looking for. I was actually giving a talk at a conference and I couldn't find this. It was pretty annoying. All right, so here is one of the many looking glass servers that lets you mess around with people's routers on the internet to some extent so you can learn about things. And here's Cisco CLI access. I can have direct access to a real router on the backbone of the internet, which is pretty nice. So I'm going to run Telnet, which Windows 7 wisely disapproves of, but it will do. And theoretically, oh good, I'm in. It tells you log in with username rviews. Okay, and I am not in privileged mode, which is pretty good because I really don't want to trash this poor guy's router. But I can do a few things even in unprivileged mode here. And there they are. And one of the things I can do is show IP BGP. All right, if I can type, it's real slow to respond. It fouls me up. Show F8. What's that do? All right, here's show IP BGP. Let me, and there we are. So this is showing you the beginning of the entire IP version 4 BGP table for the backbone of the internet. And it does have some large aggregate routes. 1900/16 can go to any of these places. Here's the list of AS numbers it's going to go through to get there. These are the names of the service providers it's going to hop through. And then here's the header again. Here's another one, 111.128.0/17. And that's just beginning to give you a taste of what I told you. There are 400,000 of these routes on the backbone of the internet, and they're all messed up. There's /16s and /17s and /23s and every blasted thing in between. and it is really a mess. But that's the way the backbone is, and it's constantly changing. And that's another fun thing to know here, of course. I mean, I've been telling students about this in general terms for years, but I was really charmed to see a good way to do it. So let me just get some of this in my clipboard. Okay, copy. We throw it in Notepad so I can trim it. Okay. There, believe that's my command. That's it. Okay, let's put that in a command prompt. Like this one will do. Okay, telnet. There we are. This is somebody at Colorado State, and they were kindly enough to hand us their BGP updates. These are things changing on the IP version 4 BGP, and every single one of them is a huge XML update. And you can see them if you, sometimes late at night it doesn't change this fast, and you can actually see things. Here I'm going to have to right click, edit, select all, right click, hey, right, all right, select all, enter. I think that might have done it. Now I think I can put it in here. Yep, there it is. So now this is something that's going to quit moving long enough for me to take a look at it. And you can see the joy of BGP4 updates. There, BGP message, there you are. Here's the end of one and the start of the next one. BGP message. Now I could use search, and maybe I better just use search because this is really hard to read. BGP message. Find next. Find next. Okay, that's the end of that BGP message right there. Now let's turn on wrapping. Okay, and now I should find somewhat tidily there's a BGP message. There's the one I wanted to get to. And it goes down there. So there, that's the end of it. That mess on the screen is one BGP update, which means that somewhere on the planet, somebody's interface went up or down. And it had an effect on the BGP routing table. Anyway, that's the current state of the mess. 400,000 routes changing that fast. That's what's delivering everything. And the miracle of IP version 6 will alter that situation. And here is the entire IP version 6 Border Gateway Patrol table the way it is right now. And that's the whole thing. It's big, but it's not that big. 2,000 routes. And you can hover over these things to see more. This is Hurricane Electric, the same guys that are giving you a certification test. They're kind enough to give you this list. If you hover over that, it will tell you here's NASA someplace. There's their route, 2001 4D09700::/40. That's an aggregate route. Remember, each company gets a 56. A whole regional internet registry gets a /23 to split up. So NASA got a /40, and there it is. It's been, I guess, 76 days since that's changed or something. I'm not quite sure. And I don't really know all the formats. I don't quite see the AS number, but the AS number is over. Here's an AS number, but maybe you're allowed to have names instead of AS numbers now. I'm not quite sure about this. I thought everybody had to have an AS number, but maybe not in BGP for IP version 6. By the way, I was just reading a book about BGP. BGP sort of supports IP version 6. It can transmit information about IP version 6 routes in the updates, but the router IDs only have 32 bits. So every router has to have an IP version 4 global routable address, and that's going to be its BGP identifier even when it's 100% IP version 6. Which is probably not that big a deal because there aren't that many backbone routers. Anyway, it's not 100% converted to IP version 6. But anyway, there's the whole BGP table. It's only 2,000 right now, but you can't reach everybody on IP version 6. A lot of people aren't playing the IP version 6 game yet, so it will supposedly expand to 20,000 when it has to route the entire current internet. Anyway, so I thought I'd show you that stuff. That might be good, clean fun. And so charge ahead with your certificates some. I'll come back later and talk some more, but that's enough of this lecture for a while.